What is going on, guys? It is your boy Pete talking about Raoul's Lock
Psych!
today. Today we got Mike.
Hey guys, this is Mike here, and today I'm going to be talking to you about the Sandwich Theorem. This is really important in calculus, especially in some of the more difficult problems involving limits, and you'll see it has lots of different uses and lots of different names. And as you'll see, it has a few different names and some different uses. So the first thing we're going to talk about is, obviously, sandwiches. So if we take a look at our sandwich here, you can see that it's made up of three parts: the top bread, the contents, and the bottom bread. Now imagine that each of these three parts represent a different function. So let's say you have g of x, f of x, and h of x. Now, if you take the limit of each of these three functions, basically what the theorem says is that if the top bread reaches a limit L, and the bottom bread also reaches that limit, then the middle contents will go to that same number. Now, this kind of makes sense because if you take a sandwich and you bring it with you somewhere, you're obviously holding it by the top and by the bottom, but the middle of it also goes with you. It doesn't just fall out of the bread. So basically, these two outer functions are sandwiching the middle one and making it go to the same limit. Now, the more formal definition is that, again, if we have these three functions, and f of x is always in between g of x and h of x, and also if we know that the limit of g of x and the limit of h of x as x approaches a is L, then we can safely say that the limit of f of x as x approaches a is L. Now, this theorem is very important. As you'll see, it's used in a few different problems, but it also has quite interesting names. The first of which is the Sandwich Theorem. So I just talked about that. It makes a lot of sense because the outer functions are kind of sandwiching the middle one. The other name is the Squeeze Theorem, or the Pinch Theorem, and that also makes a lot of sense because the outer functions are sort of squeezing the middle function into the same limit. And the last name is the theorem about two policemen. And that's kind of cool because, if you're in handcuffs and you're being held by two policemen, and let's say they're going somewhere, like the police station, well, sorry, bud, but you're also going to the police station. So these different names all illustrate the same concept. Now let's look at a practice problem. So let's say we wanted to find the limit of x squared times sine of 1 over x as x approaches 0. Now, if you try to plug in x equals 0, you might say, well, oh, that's easy, it's just 0, because x squared is 0, and 0 times anything is 0. But really, it's not that simple. So, we can definitely say that sine of 1 over x is between negative 1 and 1. And we can say that because that's basically how sine of anything is defined. The range of sine of anything is from negative 1 to 1. So we can write that. The next thing we can do is multiply through by x squared. And what this does is creates three different functions, as we had before with the sandwich. So you have negative x squared, and x squared on the outside, and x squared sine 1 over x in the middle. Now, you can treat these three as our g of x, f of x, and h of x. So, if we know that the limit of the outer functions is a number, then we know that the limit of the inner one is a number. And we definitely know that the limit of these red functions is 0, because if you plug in 0 to negative x squared and x squared, you'll get 0. So, because of the sandwich theorem, we can say that the limit of this middle function is 0. So that's how you basically formally show this limit, even though you might intuitively know that it's 0, but this is how you do it the more correct way. Now, another practice problem involves another trigonometric function, which is cosine. So what if we wanted to find the limit as x approaches infinity of cosine x over x? You might assume that it's 0 because, the denominator is really small, so it's gonna approach something really small, but we have to do this formally. So let's go through it. So again, as with the previous problem, we can write that cosine x is between negative 1 and 1. That's just the amplitude of the function. We can write that for sure. What we can do next is we can divide through by x. So this leaves us again with three functions: negative 1 over x, cosine x over x, and 1 over x. Now these can be treated as g of x, f of x, and h of x, again, like in the sandwich. So, since we know that the limit of the outer two functions is a number, then we can say that the limit of the inner one is a number. So, if we plug in infinity into the red functions, we get that the limit is 0. And it makes a lot of sense because if the denominator of 1 over something is huge, then the number will get increasingly small, and we say that it approaches 0. So, because of the sandwich theorem, we can say that the limit of cosine x over x as x approaches infinity is also 0. So that's basically how you use the sandwich theorem to prove these somewhat complex limits, and it can be used a lot in calculus, and it comes in handy a lot when you need to formally prove things. So that's it for today. I'm Mike from A3Academy. Thanks for watching, and as always, the more you know, the better you are.